All right, let's dive in. Today we're getting into Chapter 11, which is called Speech Sound Disorders in Selected Populations, and it's from the book An Introduction to Communication Sciences and Disorders. We're going to look at what happens when that ridiculously complex system, the one that turns a random thought into actual words, just doesn't work right.
So let's get right to it. Stop and think about that for a second. An idea pops into your head, and almost instantly your body orchestrates this perfect symphony of muscle movements to say it out loud. It's like this incredible biological chain of command. But what happens when one of the links in that chain snaps? That's exactly what we're going to explore.
And we're going to follow that chain step by step. First up, we'll talk about the brain's blueprint for speech, the master plan. Then we'll see what happens when the actual hardware, the body's speech machine, just can't execute the plan. And finally, we'll look at the feedback loop, because hey, if your system is getting bad information coming in, it's never going to learn to fix its own mistakes.
Okay, so let's start at the very top. The brain's motor plan. This is where the instructions for every sound you make are written. And when something goes wrong here, it's not because the muscles are weak or anything like that. Nope, it's because the blueprint itself is messed up.
This brings us to something called childhood apraxia of speech, or CAS. And honestly, the best way to think about this is like a software glitch in a computer. The brain knows exactly what word it wants to say, but the programming that tells the mouth how to form that word gets totally scrambled in translation. The hardware, the muscles and tongue, totally fine. It is a bug in the code.
So what does this software glitch actually sound like in the real world? Well, the experts have agreed on three main giveaways. First, the mistakes are completely inconsistent. A kid might say a word perfectly 1 minute, and the next time it comes out totally different. Imagine how frustrating that must be. Second, the transitions between sounds are really choppy and slow. And third, the whole rhythm and melody of their speech, what experts call prosody, is just off.
And this quote from the book just nails it. Spatiotemporal parameters. Yeah, I know, it sounds super technical, but all it really means is the where and the when of movements. With CAS, the brain's GPS and stopwatch for the mouth are basically on the fritz. It's a sequencing and timing problem, plain and simple. So here's what you really need to remember for this section. Apraxia is a planning problem. It's that software bug. The errors are inconsistent because the code gets jumbled differently each time. Now hang on to that thought, because the next thing we're going to talk about, dysarthria, is the opposite. That's a muscle problem, a hardware issue. The errors there are consistent and predictable because the physical part is broken in the same way every time. Let's go look at that hardware now. All right, so now we're moving one step down that chain of command. The brain has sent out a perfectly good blueprint, but what happens if the machine itself, the muscles, the parts of the mouth, can't actually carry out the orders? This is a full-on hardware problem.
A textbook example of a hardware issue is cerebral palsy. It's a motor disorder, and you can see here how different kinds of muscle problems lead to totally different speech patterns. If you have spasticity, your muscles are super stiff and tight, which makes speech sound really slow and strained. With athetosis, you get these random, involuntary movements that just wreck the flow. And with ataxia, it's all about incoordination, which can result in what's often described as drunken speech. You see the pattern? There's a direct line from the physical problem to the sound that comes out.
Cleft palate might be the most straightforward example of a hardware problem there is. There is a literal physical gap in the roof of the mouth. The machine itself wasn't built to spec, which can make producing certain sounds, especially ones that need you to build up air pressure, pretty much impossible.
But here's the thing. The human brain is an amazing problem solver. If it can't make a puss sound at the lips because there's a gap, it'll figure out a workaround. And these workarounds are called compensatory errors. Essentially, the person starts making sounds way, way back in their throat where they can build up that necessary air pressure. It's a really clever fix for a hardware flaw, but it often makes their speech incredibly difficult for others to understand.
And this little bit of technical jargon perfectly describes that workaround. Posteriorly and inferior just means further back and lower down. So instead of making a sound at the front of the mouth, the speaker is literally shifting the entire production line backward to get the job done.
And all of these hardware issues, they fall under that big umbrella term we brought up before, the dysarthrias. They're all about neuromuscular problems, and this chart just gives you a little taste. Depending on where the nerve damage is, you get completely different results. Damage that makes muscles too tight, you get that strained, spastic voice. Damage that messes with coordination, you get ataxic speech.
And damage that makes muscles weak and floppy, you get a flaccid, breathy voice. So we've looked at the blueprint, and we've looked at the machine, but speech isn't just a one-way street from brain to mouth. The whole system depends on a constant feedback loop. You have to hear speech to learn it, and you have to process what you're hearing to make it better. So what happens when that feedback loop is broken?
This one's about as intuitive as it gets. If you can't hear the sounds of a language correctly, especially those really subtle, high-frequency sounds like s or f, how on earth are you supposed to learn to say them correctly? A hearing impairment basically starves the brain of the good, clean data it needs to build a functional speech system.
And of course, this isn't just an on or off switch, right? It's a spectrum. With a mild hearing loss, maybe you just have trouble with a few consonants. But as that loss gets more and more severe, the problems just pile up. You go from having a few sounds that are off to most of your consonants and vowels being affected, all the way to a profound loss where even the basic rhythm and pitch of speech are gone because the person is getting basically zero auditory feedback.
Now, what if the hearing is totally fine, but the brain itself struggles to process the information it's getting? That brings us to intellectual disability, or ID. It affects about 1% of the population, and this isn't about bad input, like with hearing loss, and it's not bad hardware, like with CP. This is a limitation in the brain's central processing unit, its core ability to understand and learn complex systems, like, say, the rules of a language.
So what does this actually look like? Well, a lot of the time, the speech development just looks like that of a much, much younger kid. It's delayed. But it can get trickier. The source material points out that for some folks, like individuals with Down syndrome, the speech patterns can be both delayed, so they're on the right path, just way behind schedule, and also deviant, which means they're making errors you wouldn't typically see at any stage of normal development. It really shows you how much this all depends on the brain's processing power.
Okay, let's zoom all the way back out and put these pieces together. We've walked through the entire chain of command, from the initial thought all the way to the spoken word.
So, if you take away one single thing from all this, let it be this. A speech sound disorder is not one thing. It can be a failure at any of three key points in the system. It can be a problem with the blueprint, the brain software, like we saw with apraxia. It can be a problem with the machine, the body's physical hardware, like with cerebral palsy or a cleft palate. Or it can be a problem with the feedback loop, where bad data coming in or faulty processing means the system just never learns to work right in the first place.
And that leaves us with one last thought. We've just gone through all these different ways the system can break down, in the plan, in the execution, in the feedback. When you really stop and consider the sheer complexity of it all, the incredible speed and precision that every single sentence demands, doesn't it make you wonder? Maybe the real miracle isn't that speech sometimes goes wrong, but that it ever goes right at all.